Welcome to Study Loop.
In this problem, we have a satellite of a given mass which is launched into a free flight trajectory about the Earth. We have the initial speed and the initial launch angle which are given, and we want to calculate the closest distance the satellite is from the Earth, as well as the speed of the satellite at this distance. So we'll first use the conservation of angular momentum about O. So the conservation of angular momentum about the center of the Earth, point O, at point A must be the same as the angular momentum at point B. Now, the initial angular momentum of the satellite is mvr, so that's the mass of the satellite times the component of velocity, which is perpendicular to r, so that's va sine of phi a times ra, and this must equal to the angular momentum of the satellite at its closest distance to the Earth, at which point v and r are already perpendicular. So this must be m times vb times rb. So substituting our values in here, we get the mass of the satellite, which is 700, times va, which is 10 kilometers per second, so that's 10 times 10 to the power 3, times the sine of the launch angle, 70 degrees, times 15 times 10 to the power 6 meters, which is Ra. That's the initial angular momentum of the satellite about the center of the Earth. The final angular momentum is the mass of the satellite, 700 times Vb times Rb. So we have an equation here with two unknowns. We'll label this equation 1. Now we'll apply the conservation of energy. The kinetic energy plus the potential energy at point A must equal to the kinetic energy and potential energy at point B. So TA plus VA must be equal to TB plus VB. That's the conservation of energy. The initial kinetic energy is a half mv squared. It's half times the mass of the satellite times its speed at A squared, minus its gravitational potential. Its gravitational potential energy is universal constant G times the mass of the Earth times the mass of the satellite divided by the separation between them, Ra. This must equal to the kinetic energy at point B, a half ms v b squared, minus the gravitational potential energy at point B is again G me, mass of the Earth times ms, the mass of the satellite, divided by the separation at point B, which is Rb. Now we can substitute our values again into this equation, and we get half into 700 into 10 times 10 to the power 3 all squared, minus the gravitational potential term, where G is 66.73 times 10 to the minus 12 in SI units. The mass of the Earth we are given as 5.976 times 10 to the power 24 in kg, times the mass of the satellite, which is 700. This is all over the separation at Ra, which is 15 times 10 to the power 6 meters. And this must equal to the right-hand side, which is a half into 700 times Vb squared minus again 66.73 times 10 to the minus 12, which is g, times 5.976 times 10 to the power 24, and the mass of the satellite 700, all over the unknown distance rb. Now this equation also has two unknowns, which are the same as equation 1. We'll call this equation 2. So if we solve equation 1 and 2 simultaneously, we get that we can find VB and RB, and we get VB to be 10.2 kilometers per second, and the distance RB to be 13.8 megameters.